Imagine waking up in a city where traffic lights adjust automatically to traffic flow, where streetlights brighten only when people walk nearby, and where artificial intelligence quietly manages energy, transportation, and safety. This is not science fiction. This is the world of smart cities. Across the globe, engineers are redesigning urban life. Using sensors, data, automation, and artificial intelligence, these technologies are transforming how cities operate, making them more efficient, sustainable, and livable for millions of people. Cities like Singapore and Barcelona are already pioneering this transformation. But how exactly does it work? Let's explore the incredible engineering behind the cities of the future. At the heart of a smart city is a digital nervous system collecting data to optimize every service. This architecture relies on the Internet of Things, or IoT, a network of networks. It connects roads, traffic lights, buses, buildings, and even waste bins into a unified ecosystem. In Singapore, GovTech manages the Smart Nation Sensor Platform. A key component is the Lamppost as a Platform initiative, turning streetlights into data-gathering hubs. Barcelona utilizes Centello, an open-source horizontal platform. This architecture allows different agencies to share data seamlessly, fostering a truly integrated urban environment. Information travels through high-speed fiber optic networks and is processed by powerful computers and AI systems. The result is a city that can respond, adapt, and optimize itself in real time. Nowhere is this more critical than in transportation. Every year, billions of hours are wasted in traffic jams. But smart city engineering is solving this through precision data and AI analytics. Singapore's iTransport platform fuses data from ground sensors, GPS-enabled taxis, and CCTV. Their operations control center manages incident recovery 24/7 across 160 kilometers of expressways. The city's pioneer electronic road pricing system uses overhead gantries to charge vehicles based on real-time congestion levels. Under the Smart Mobility 2030 plan, laser scanners below MRT train carriages monitor track conditions in real time. Barcelona tackled parking congestion by embedding asphalt sensors in thousands of spaces. The city's digital bus shelters are equipped with solar panels and provide real-time arrival data. In the future, autonomous vehicles may further revolutionize transportation. Beyond movement, managing energy efficiently is a primary engineering challenge. Cities consume nearly 75% of the world's energy. Singapore uses machine learning and satellite imagery to forecast solar power fluctuations. The city is progressively deploying smart meters, allowing consumers to track energy usage in 30-minute intervals. Under the Green Mark scheme, over 3,000 buildings use IoT-based HVAC systems. In Barcelona, the lighting master plan turned over 1,100 lampposts into smart nodes. Safety is also critical. AI-powered surveillance systems can detect unusual activity or traffic accidents instantly. In Barcelona's Plaza del Sol, residents used low-cost noise sensors to proof excessive nighttime noise. Environmental sensors monitor air quality and pollution levels island-wide. Managing waste and water is the next frontier. Traditional collection follows fixed schedules. Barcelona has pioneered pneumatic vacuum systems that suck waste through underground pipes directly to central processing plants. In Singapore, solar-powered compactors and smart bins allow them to hold 8 times more volume. Water management also benefits. Sensors installed in pipelines detect leaks immediately, preventing massive water loss. These engineering investments yield quantifiable returns. Barcelona estimated its smart initiatives saved $58 million on water. The cities of the future will use digital twins, virtual replicas used for simulations and planning. By combining engineering, data, and AI, smart cities promise to improve quality of life for billions. Barcelona transformed its mobility, focusing on efficiency and user experience. To reduce the 30% of urban traffic caused by drivers searching for parking, Barcelona embedded asphalt sensors in thousands of spaces. These identify occupancy and relay it to the AparkB app, which also handles digital payments. Within 1 year of launch, the city was issuing 4,000 parking permits daily via the app. Barcelona's bus shelters are equipped with solar panels and interactive touchscreens. They provide USB charging, free Wi-Fi, and real-time arrival data. Beyond movement, managing energy efficiently is a primary engineering challenge. Cities consume nearly 75% of the world's energy. Smart grids are the solution, automatically balancing supply and demand. Sensors monitor energy consumption in homes, buildings, and industries. Singapore's challenge is managing the intermittency of solar power in a high-density environment. In 2024, the Energy Market Authority commissioned an enhanced energy management system. It features a solar PV forecasting model that uses machine learning, satellite imagery, and island-wide irradiance sensors to predict solar output fluctuations. This allows the grid to adjust reserve power proactively, managing the intermittency of renewable energy. Singapore is progressively deploying advanced metering infrastructure, allowing consumers to track consumption in 30-minute intervals via the SP Utilities app. Under the Green Mark scheme, over 3,100 buildings are certified, which mandates IoT-based HVAC systems. Startups in Singapore have demonstrated up to 40% energy savings by using algorithms to direct cooling only to occupied areas of a building. In Barcelona, the lighting master plan turned over 1,100 lampposts into smart nodes. These lights dim automatically when streets are empty, yielding 30% energy savings across the system. Beyond lighting, these poles act as Wi-Fi hotspots and environmental monitoring stations for air quality and noise. Safety is another critical component of smart cities. Advanced surveillance systems powered by artificial intelligence can detect unusual activity and alert authorities immediately. Smart cameras can identify traffic accidents, suspicious behavior, or emergency situations. This allows emergency responders to react much faster. Environmental sensors also monitor air quality and pollution levels. If pollution rises above safe limits, the city can automatically trigger responses such as restricting vehicle traffic. In Barcelona's Plaza del Sol, residents used low-cost noise sensors provided by the city's Fab Lab to prove that nighttime noise exceeded WHO recommendations. They successfully lobbied the council to change the plaza's usage hours. This demonstrates the bottom-up data democratization that characterizes the Barcelona model. Managing waste is another major challenge for growing cities. Traditional garbage collection follows fixed schedules, but in smart cities, waste bins contain sensors that detect when they are full. Barcelona has pioneered a pneumatic vacuum waste collection system in many neighborhoods. Residents drop waste into smart bins. The system then sucks the waste through underground pipes to a central processing plant. This eliminates the noise and emissions of garbage trucks. For traditional bins, IoT fill-level sensors optimize collection routes, reducing fuel consumption and operational costs. Singapore utilizes solar-powered smart bins equipped with internal compactors. These bins can hold up to 8 times more waste than standard bins. Sensors alert the waste management team when a bin is full, preventing overflows. Additionally, the MyENV app uses gamification to encourage citizens to report littering or full bins, turning the public into a human sensor network. Water management systems also benefit from smart technology. Sensors installed in water pipelines detect leaks immediately. This prevents massive water loss and reduces infrastructure damage. Cities such as Barcelona already use smart irrigation systems that adjust water usage based on soil moisture and weather conditions. This saves millions of liters of water every year. Flood sensors installed in rivers and drainage systems can detect rising water levels and send early warnings to prevent disasters. These technologies help cities become safer and more resilient. The engineering investments have yielded quantifiable returns. Barcelona estimated that its smart initiatives saved $58 million on water, and increased parking revenues by $50 million annually, and created 47,000 new jobs. Singapore maintains car speeds nearly double those of other major regional capitals despite having one of the highest population densities in the world. The smart cities we see today are only the beginning. Future cities may include fully autonomous public transportation, AI-managed energy systems, and buildings that generate their own power. Drone delivery networks, and digital twins, virtual replicas of cities used for planning and simulations. Engineers are working to create cities that are not only smarter, but also more sustainable. By combining engineering, data, and artificial intelligence, smart cities promise to improve quality of life for billions of people around the world. The cities of the future will not just grow, they will think, adapt, and evolve, and the engineering behind them will shape the way humanity lives for generations to come. The future of cities has already begun, and it is being built, one smart system at a time. As cities become more connected, the engineering focus must shift toward security. Cybersecurity is the foundation of every smart city system. Engineers implement multi-layered encryption and robust data privacy protocols to ensure that the vast amounts of citizen data remain anonymous and secure. Resilience is built into the architecture through redundant systems and decentralized networks, protecting critical infrastructure from potential cyber threats or technical failures. The implementation of 5G and edge computing is the latest engineering breakthrough. By processing data closer to where it is collected, latency is reduced to near zero. This ultra-low latency is what allows autonomous vehicles to communicate with traffic signals in milliseconds, making our streets safer and more predictable. Engineering standards such as ISO 37120 provide a global framework for measuring city performance and quality of life. These standards ensure interoperability, allowing devices from different manufacturers to communicate seamlessly within the same urban nervous system. But technology alone is not enough. Engineers must also address the digital divide, ensuring that smart city benefits are accessible to all citizens, regardless of their technical proficiency. The goal is to build equitable infrastructure that empowers the community through data transparency and inclusive design. The cities of the future will be defined by their resilience, the ability to think, adapt, and evolve in the face of climate change and rapid urbanization.